Hello again, folks, in 114. Today we're going to be covering section 12.4. Boy, I didn't do it again. Okay. Today is naturally Thursday, June 24th. So we're covering section 12.4 to confirm that. All right, notice we're near the end. Which is cool, right? Let me show you the packet. The packet consists of this overview made for variation, which is what this section is about. This original copy here, I actually changed, I added some numbers. You'll see when it's projected, but there's the formulas at the bottom and a list of procedures and what they would be used for. This is from the textbook. I just printed this in black and white because I'm trying to save my color. But your copy is in color if you'd like. This is the same information, it's just not in a diagram. Let's see. Then there are some examples, some of which I took from another resource. I like this one especially. I'll get into that in a moment. There's a little bit, it's kind of a worksheet the way I made it so you can see how these things compare. Then there is the process broken down for calculating variation, variance, and standard deviation. All right. Maybe just do this one time to get a feel for it. But in reality, what you'll be using is your calculator primarily to calculate either of those, or an Excel spreadsheet. Now, I again sort of broke down the same information. You could write this in this blank of the Excel spreadsheet, and then you can see how it evolves into standard deviation, or simply use, there's a function naturally in Excel that you just type stdev parentheses and then the location of the data, and it will just do it for you. But I think it's easier for a person to understand if you pick it apart. So I'll do that one time. There's a copy of the spreadsheet if you want to use it as well. And then there are the actual examples that are from your textbook. Okay, so we'll go through those. All right. Takes a little getting used to, but it's actually really interesting. Let me turn on the projector here, and we'll get rolling. Center the camera. Yeah, it has to be moved over slightly. All right. Nope, don't do that. What's going on here now? All right. That's better. Okay. Minimize this. All right. Here's our overview of chapter 12 once again. So you see where we're headed, where we've been. Here we were in 12.1, gathering, organizing data. Here we were in 12.2. Types of graphs, basically the presentation aspect of it. These two is section 12.3, that was yesterday, and now we're in section 12.4. All right, types of variation. Okay. Let's see. All right, as for those, here's a diagram to summarize. All right, this is what I was mentioning earlier. I had put some numerals here to follow a train of thought in a certain order. I better close this window. It's going to fight with me. I'm doing that because it gets hot in here. All right. Let's free up some space here. All right. Just like types of averages are meant to give you a feeling for where the center of data is, all right? Think of types of variation as giving you a feel for how different data is, one data set from another. Now, it would not be a fair comparison unless certain conditions were met. Incidentally, here's the mean formula, which will be important later, just for the sake of comparison as well. There's mean of a population, and we use the abbreviation X bar. And then there's mean of a sample is X bar, mean of a population is in red, and that is the mu symbol, right? There are similarly abbreviations for sample and population when we get to standard deviation. Okay. The fair comparison is really here, right? I'm jumping the gun a little bit on the variance. When comparing sets of data with a similar mean, all right? You could calculate the range or the variance or the standard deviation of any sets of data, all right? But it maybe isn't really understandable unless you're comparing it to something else, all right? A second set of data in which you calculate a range, a variance, or a standard deviation. Bear this in mind because it's important, all right? You use variance in particular, all right, when comparing sets of data with a similar mean, all right? So their average has to be basically close. Doesn't have to be exactly the same, but it's close, all right? What's more intuitive maybe is this concept of variation, all right? Range, all right? It's calculating the total spread, how far apart the lowest piece of data is from the highest piece of data, all right? And it's just subtraction, right? You use this when the total distance is sufficient enough information and or the data are evenly spread, right? That is, if you, from one point to another, there's basically almost the same distance apart, all right? There's no outliers, that is, there's no suspiciously large or small data value in the set. It's not skewed in any way, the spread, all right? This is the easiest to calculate, but it's also the least reliable because it is in fact susceptible to outliers, right? Right. If you're trying to get a feeling for how spread the data is from one data value to another, you want some consistency. You don't want one data value that's throwing you out farther than most of the data actually is. Okay. Now again, there's a formula or just a procedure here you see. In which case you subtract the lowest value from the highest value. This would, remember, it's not commutative. It's the high value minus the low value. That will just simply give you the range. All right. If you do in fact have an outlier, then this can be a deceptive value. All right, and it's not really good for giving you a feeling for anything. All right. Let's go over to variance. All right, for a moment. As I said, you use this when comparing sets of data with a similar mean. You know that information ahead of time, and you don't care about the units per se. All right. The thing about variance is that it's not going to give you an answer that is in the same degree as the data itself. Right. Here's the little tip-off of that. You really do square the standard deviation. Right, and the standard deviation entails this procedure, which we're going to get to. That's really the meat of this entire section. All right, it's really going one extra step. All right, so if you had the standard deviation already, then you square it, and that will give you the variance. All right. Again, this is just for the sake of having, an idea of how spread apart the data is. Again, you only do this when you have two sets of data when the mean is about the same. All right. All right. Now, as for the standard deviation in which these things are related, you see this is a more complex formula. All right, and this is the whole kit and caboodle at the same time, summarized. All right. Bear in mind, you could calculate a standard deviation, all right, of a sample, in which case it's usually just abbreviated S. Even in your calculator, all right, that will be written as such, S. Or the standard deviation of a population, which is abbreviated by a lowercase sigma, sort of the Superman, bouffant, what do you call that, spit curl, Anyhow, you use this when a more reliable measure of spread is needed, more reliable than the range, right? How it goes about the process is that it takes into consideration sort of an average of distances, right? But you need to identify what the frame of reference is. The frame of reference, that is the starting point for which you compare other things, will be the mean, all right? That's why I mentioned the mean formula up in here, all right? It's the spread, the average spread from the mean, which is hopefully the center of data, hopefully, all right? The greater the variability, the larger the standard deviation. So if the data are very far apart from one another, you should expect a larger number, all right? If the data are right on top of each other, all right, then you'll expect a smaller standard deviation, all right? Just realize that this common point, all right, if the mean in the ideal situation, and it isn't always, of course, ideal, if the mean is dead center, all right, then any other data value that you have, all right, is going to be compared back to it, all right? Those distances. Distance to and from the mean is essentially the idea of a standard deviation, all right? And then it takes more or less an average. Now, here's how so. All right, it's, as I said, I'm going to go through this the brute force way first. You start by calculating the mean, all right, and then you subtract each value from the mean. Now, what's going to end up happening is that in some cases, depending upon what the data value is, you're going to get a pile of positive numbers and negative numbers, all right? Because if this number is larger than the mean, which implies that it is to the right of it, all right, then you'll get a positive answer, even when you subtract. If this value is smaller than the mean, then you're going to get a negative number, all right? When you normally take an average, what do? You add up all of the figures that you produced or what are given to you, all right? But there's going to be, unfortunately, a kind of cancellation effect, all right, if you start trying to combine positive values with negative values. So to circumvent that, all right, math people have decided that, well, how could I avoid a negative entirely, all right? Remember from arithmetic, right? If you square a value, whether it starts out negative or positive, what's going to happen to the sign, right? It's going to produce a positive only, right? So that's a way of circumventing the cancellation effect, all right? For the sake of, again, we're trying to sort of average. Standard deviation is kind of an average unto itself, but it's the average to and from the mean, all right? Then we do what we do, which is adding these squares, all right? And then depending upon whether you want a sample or a population, you take the sum that you have added and then either divide by one less than the total number of data or the exact total, right? If you divide by the exact total, then you have a population, all right? If you divide by one less, then you have a sample, okay? This is the formula summarizing that. Now, in order to basically undo what has been done for the sake of avoiding a cancellation effect, the opposite operation, square root, because opposite of squaring is square root, is then applied as the last step, right? So whatever this quotient ends up being, as an afterthought, it's square rooted, right? And then you get this. This is standard deviation, a sort of average of distances to and from mean, all right, in summary, all right? Now, as I said, the variance is more or less the original idea, but it doesn't have this added step involved here, which is why squaring it would be undoing this last step if you were going to do it, you know, as an afterthought, okay? Basically, if you went this far in the procedure, not step 6, you'd have variance, right? If you then went a 6th step, which is the square root, again for the sake of undoing a cancellation, the squaring portion of this, which itself was for the sake of avoiding cancellation when you add, all right, then you could get back to standard deviation, right? These are just one step apart, essentially, right? But think of this as more or less the original idea. The only downside to it is that if you stick with variance, all right, you do not have the unit in the same degree, all right, because you squared something. This is undoing that. All right, that's why I added this notation here. Variance is one step away from the standard deviation. It's just that the units do not match the units of the data, right? And that maybe makes you uncomfortable. It makes me uncomfortable. All right, so you would end up with units squared if you calculate it technically, a variance only, versus this would be a unit in the degree that you started with. Right? Units first degree versus units second degree. Okay, so that's an overview, and again, these are the formulas, all right? Let us look at these word problems that I have here, all right, to get your feet wet. I rather like this because there's some dogs here. And one of them is a Bernese mountain dog, which I used to have a dog named Pocono. And he looked like that. There's a good dog. Okay, now, if the idea of variation is to give you a feeling for how spread apart the data are, right? This is a visual aid, right? Now, granted, there's less dogs here than in this picture. There's quite a few more, all right? But you could see superficially, all right, that if you think of the individual dogs as being data values, right, that they're not drastically different in terms of their size, all right? And really, to be a fair comparison, we really would be comparing their weight. So these two guys over here are probably the heaviest, all right, since they're all dogs, right, and they're based upon the same anatomical model of, you know, flesh and blood and bones and what have you, all right. These two guys are probably the heaviest, all right, and these two guys are probably a little bit less, but not drastically different, all right, versus if you were to compare these guys in here, all right, there's more variation in terms of their weight, all right. Here you have what appears to be a Scottish Terrier, right? There's a little tyke there sitting. And a Siberian Husky, I'm going to go ahead and guess, not a Malamute. Basset Hound, all right? A Bernese Mountain Dog, my boy Pokey, who I loved. And that looks like another Basset Hound, but it can't be. It's probably something similar. All right, thinking either an Irish Setter or a Golden Retriever. Dalmatian, and a bulldog. So I could definitely vouch for the Bernese being quite heavy because I used to have to pick them up sometimes. Anyhow, let's do a couple of calculations here to get the point across. All right, the set of weights measured in pounds was just thinking about what we're used to here in the United States. All right, for these four dogs is 70, 73, 58, and 60. Right, meaning that this Weimar, I think that's what you would call this dog. Weimaranian or something like that. He's probably the hefty one. 73. All right. To be a good sport, I mean, you really should put these in numerical order, but it may not be imperative. All right. We're going to calculate the mean first of each of these, and then we'll calculate the ranges. Okay. This is a basic exercise. Okay. So if you remember the formula, all right, I'll put it in green because it's usually faint anyway. All right, the average mean is the sum of the data divided by the number of data. All right, so that means the sum would be 70 plus 73 plus 58 plus 60. And the number of dogs is 4. All right. And just to expedite here, let's calculate. All right. 70 plus 73 plus 58 plus 60 gives you 261. Divide by 4. 4 goes into 26 roughly 6 times, with 2 left over. Goes into 21 roughly 5 times, with 1 left over. Goes into 10 roughly twice, with 2 left over. So 65.25. Right. I'm going to move this up now, and I'll just write the value here. The average is 65.25. Okay. If we were to calculate the range, this is the reason why you might want to put this in numerical order first. It would be 58, then followed by 60, 70, and 73. Right? This would be the low value, and this would be the high value. All right. The range would be 73 minus 58, which is how much? 225, it looks like, right? 15 rather. Yeah, 15. All right, so 15. All right. Now, let's calculate the mean here. All right. And in this instance, let me go through the exercise of calculating via your calculator, right? The average. All right. We're still going to do the same thing. We're going to calculate a mean and a range here and here. But we'll take advantage of this. Okay. Okay. You don't have to put it in numerical order to start with, but you should go through the process of clearing out whatever you have. So remember, hit second and then data, and scroll over to the end to underscore clear data, and then hit enter. And now you're free to do what you want. The setting is already on one variable statistics. So we're good to go in terms of that. I'm going to hit it out, that equals again. Now when you press data, there should be voids for entering X1, first data point, X2, second data point, and so forth. All right. These are not in numerical order, but they really don't have to be. All right. When you're entering them, just be careful that you cover them all. 60, 85, 42, 125, 40, 75, and 30. There should be 8 total. Just to show you what this looks like, this is the 8th data value. 75, 40, that's over here. 125, 45, 42 rather. 85, 60, 55, right? Now, when you press stat var, it'll calculate the mean for you, among other things, all right? So I'm gonna hit stat var, and you see 8 values for n, and there's an x bar value here. So there you have it, 64 exactly, all right? The point of this is, again, the exercise is going to be especially useful when you calculate standard deviation. You probably do not want to do that by hand. I'm going to do it one time just to show you how it evolves. But here you see means that are relatively close. These two data sets have similar mean. So it's a fair comparison, all right, to compare these sets of data, all right, via, say, variance or standard deviation, all right. I'm just doing ranges right now because that's to introduce the concept. Notice what's going to happen, all right. If you calculate the range here, all right, you get 15. If you calculate the range in this more plentiful set of data, all right, what's the high value? It would be 125 minus the lowest value appears to be 30, and in which case you get 95, right? All right. So what does this mean? It means that the extremes are 15 apart, whatever that unit is, 15 pounds apart. All right. And in this instance, the extremes are 95 pounds apart. All right. All right. So, let's do another problem, and I'll show you how to work your way through the standard deviation. I already have on the calculator here, I don't want to give away the story yet, but I could give you the standard deviation of the sample or of the population if I just scroll over, but it's only for one set of data. So let's see what it is for the population here. $28. You're not asked to calculate this, but it is interesting. The standard deviation of this population is about 29. I round it to a whole number. 29 pounds. If I did it for this set, it would be less complicated, but I'll do it really quickly. I'm curious. Bear with me 1 second. I'll clear the data. And then I'll enter 70, 73, 58, and 60. You'll see that here. 4 sets of data for the original set. Here's the average, 65.25. And if I go to population here, 6.3, almost 6. Okay. This standard deviation is arguably a more reliable figure because it's not just taking the two extremes into consideration, which again, it would be susceptible to an outlier, all right? What you have instead is a comparison to the center, right? Remember, the standard deviation is the average of the averages, if you will, right? Well, the average pardon me, let me rephrase. It's the average of the distances to and from the average, which is the mean, right? The middle, all right? So you have everything is compared to the same center, all right? Anyhow, it's an alternative to taking a range, all right? In these cases, all right, maybe it's not such an unfair comparison, all right? Range is sufficient, in other words. All right. Now, let's look at the next one here. And I broke it up into steps. The set of heights measured in inches of the top 6 players of the Cleveland Cavaliers in the 2011 to 2012 season. All right. So we have 6 players, 75 inches, 81 inches, 83 inches, 78, 81, and 74. All right. If you were going to do this more or less brute force, which is by hand, and I will only have you do this one time, I swear. It's for the sake of making you feel a little bit stronger relationship with what is going on. Right? You'll understand it better if you do it by hand one time. You'll also appreciate what the machine is doing for you. So this will pluck it apart. All right. All right. If this is the standard deviation formula, I'm just going to abbreviate it STDEV. It's the square root of the averages, but broken up like so. The sum of the data to and from the mean squared to avoid a cancellation over, if you calculate the standard deviation of the sample, it would be just minus 1 data value. You can get it instead over n if you'd like. All right. Here's how you would do that. You would take the data values that are here, 75, 81, 83, 78, 81, and 74, and start by putting them in numerical order, which is always a good habit anyhow. I'm going to, because I don't want to obscure anything, maybe back this off just a little bit. There you go. I'm going to rewrite these in numerical order. All right. So the low number would be 74. The next would be 75. I think I better turn off the water here. My sister's boiling. 74, 75, 78, 81, 81, and 83. Okay, in numerical order. You would next calculate the mean by adding all of these to establish what the middle would be, and dividing by how many there are, which is 6. And in this case, the total should be, I believe, 472 divided by 6 would give you about 78.6. The only rotten thing about this is that you're going to get a repeater. So I'm going to try to be as precise as possible, or as accurate as possible, by including this degree of precision. So I'm going to write it as 78.6 repeating. All right. If you're doing this by hand, you end up you're going to have to probably round something, but this is the reason why you would use a calculator or Excel right here, something that repeats. right? Next, you're going to try to subtract each data value to and from, or by and from the mean, all right? So that's a pain in the neck, all right? If you do that, all right, 74 minus this figure, at this point, because you're doing it by hand, you're really going to have to round. I will now round this to about 79. All right. 79 and 74 subtracted is a difference of 5, but because it would be in the order of 74 minus 79, you would end up with a negative. So this would be negative 5. All right. For your first distance to and from the mean. All right. If you did this one, 75 minus 79. All right, now it's a difference of 4. 74. All right. 78 from 79. You get a distance of 1. Now finally, once you exceed the limit of 79 and get to 81, you're going to finally get a positive. Right, the difference in that case would be how many? 2, right? So it'd be plus 2. And then it would happen again, plus 2. And then this time, plus 4. Again, you'll notice that if you attempted to more or less take an average of this much information, because half of them are negative, and half of them are positive, there's going to be a cancellation effect. It's going to undo what you're trying to accomplish. So to circumvent that, what happens is that each one of these gets squared. All right? So negative 5 times negative 5 is 25. All right? Negative 4 times negative 4 is positive 16. All right? Negative 1 times negative 1 is positive 1. And 2 squared is 4, and it happens again, and 4 squared is 16. Right. And then you would add all of these squares. Right. Let's see. You could do it in any order when you're adding, of course. Right. 16 and 16 is 32. To add to this 25 is 7. Is 57, plus another 5 is 12, carry the 1 is 6, and another 4. You should get 66 as the total sum. All right. Just to be skeptical, let me do this. 25 plus 32 times 5 times 4. 66. All right, looks legit. All right, now at this point, you're going to divide the sum either by, if you want a population, divide by 6. That's intuitive, right? If you want a sample, divide by 5, because that would be 6 minus 1 is 5. I'm going to go with, I'll do both. That's that. All right, if you divide by 6, all right, 66 divided by 6 would naturally be 11. Right. If you did 66 divided by 5, this is a pop, this is a sample. Alright, what are you going to get? 10 point something. 66 divided by 5. No, pardon me, 13. Yeah, okay. Yeah, 13.2, sorry. That makes sense, yeah. Because if it was 60, it would be 12, right? Okay. So 13.2. All right. Now, at this point, if the original unit was in inches, because this is the heights of basketball players, right? In the United States. The original unit was inches. At this point, because of the squaring that had occurred earlier, what you in theory would have here is inches squared, right, which would be an area, right, All right, whether you had taken a population into consideration or a sample. All right. So to take it one step further, to return it to the degree of unit that it would be degree 1, all right, we're now going to undo the squaring as an afterthought, essentially. So if you take the square root of 11, all right, you get what? 3 point something? You get 3.3, something like that. I'm going to write it with the abbreviation of lowercase sigma in this case, is about equal to 3 inches. And if I did it using the sample instead, the square root of 13.2 is 3.6. So about 4 inches, almost 4. All right, and in this form would be in degree 1, regular inches. All right, the rounding may or may not be necessary, it depends on the conditions, but that's the process, as you can see, and that's just with 6 pieces of data, which, as you can see, there's room for error, especially if you're rounding mid-calculation, as I had, just to illustrate. All right. So, all right, what you'll more likely be doing is taking this information and inputting it into your calculator, right? And you'll get a better answer because it will have a higher degree of precision than just, a whole number 79, right, to start with. Okay, so let's do that very quickly, and then I want to show you the Excel spreadsheet that you could use alternatively if you like. That's a good skill if you go into an office setting. All right. First things first is clear out the old data. So if you hit second and then data, scroll over here and clear it, and make sure that your setting is in, 1 variable statistics. 2 is for like section 12.5 or 12.6. Okay, we just want that. Now you hit data and you have the empty spaces to put 74, 75, 78, 81, 81, 83, what have you. Right? You don't have to put them in numerical order, but it would always be cool if you did. '81. If you want, here's an interesting point. We have two 81s, so when you get to the 4th piece of data, you put in 81, and then you could hit frequency of 2 if you'd like. And that will spare you from having to enter it again. Now, even though there's still 6 points of data, when you get to the next void, just type 83. All right. All right, that's everything accounted for. Blue screen of death. Okay, now, when you hit stat var, the button adjacent to data, it'll tell you there's 6 pieces of data, so no fear. All right. Here's the average, 78.6 repeating. All right. The 7 on the end is just your calculator rounding the last digit. All right. And then you have the sample standard deviation, and you have the population standard deviation. So I'm going to scroll over to these and compare them. All right. My estimate, not so bad. All right. 3.6. This, as you can see, is more precise though. Right. It's 3.61 such and such. I believe it was 3.63 right before I rounded it. You really shouldn't round mid-calculation. This is always a bone of contention. Here's the sample, here's the population, 3.5. That's a lot different from what I had. I think it was originally 3.3 and I rounded down. All right, so that's a little bit closer to, this is more reliable. All right, 3.2 rather. Well, you know what? I'm sorry, I'm reading it backwards. If that's 3.29, my estimate is not so bad either. All right, as you can see, it's pretty close. All right, but this is much higher precision. It has more digits here. All right, this is a more accurate result. All right. All right, and it's considerably less work. All right, especially as you're doing your MyLab work. All right, if you have to calculate standard deviations and so forth, please, all right, use your calculator. All right, no one expects you to do it, arduously. Just beyond, getting a feel for what you're doing. Okay. Now, what I want to do is just show you something else really quickly, which is how you would do this in Excel were you in that situation. Right? Here's a blank. I prepared this with headings. What you would do is take the original set of data, and you can enter it in any botchable loop order that you like, actually. But I already put it in numerical order. All right. But you would write it in the cells here, right, that you're giving the spreadsheet the data. So 74, 75, 78, 81, 81, 83, you would write in a column here, all right? 74, 75, 78, 81, 81, 83, all right? And then if you wanted to illustrate how this slowly evolves, you could just do this piecemeal until you get to either variance or standard deviation, the whole 9 yards. All right. If you're calculating just the mean, all right, you could do it brute force. All right. You could simply you could basically take write equals first, bless you, all right, and then highlight this column, and it will show up as, if this is A1, it will show up as A1 colon A6. And then divide by, 6. You can brute force type that, and it will spit out the value there. Or you could take advantage of the built-in functions in your spreadsheet, which is to type average, and then there'll be an open parentheses. You highlight this, and again, it will give you the more or less the battleship coordinates. Close the parentheses, and then it will spit out the value. All right. That will establish what would be the average. All right. Then the next thing is, again, you could hit equals, and then highlight this, A1 to A6, close parentheses, hit minus, and then because you don't want this value to change, you would hit the location of the mean, which would show up in, essentially this would be B1. So you put $B, $1 here. That represents the location of where the mean is sitting, all right? If you don't put the dollar signs, then it will automatically move to the next space, which would be blank, and that's where you get an error message, all right? Then when you go here, again, if you're doing this piecemeal, all right, you'll have, again, 6 data values. And you'll say you want the location of these, which was in theory and now in C, all right, C1 to C6, all right, upward pointing arrow, and then and hit 2, all right. Squirt, and then you get 6 values, and then you could hit sum, SUM, of the location of this, which would be D1, all right, to D6. All right, and then you, depending on whether you want variance or not, you can hit divide by 5 or divide by 6. All right. If you're going to just simply go straight for the function that is built into your calculator, built into the spreadsheet, there's 2 that would be beneficial. All right. STDEV is the thing that will automatically do this without the piecemeal results. All right. You have to hit equals always first. Average is what calculates a mean without having to tell it specifically what to do. All right. Sum, all right, is another one. The only thing that you have to get used to with Excel is that you're using coordinates separated by a colon, all right? So it will evolve, all right? This would be the start, and this would be the finish location, all right? You have to tell it where to look, all right? If you use dollar signs, something like this, put the dollar sign in front of the letter, and then the dollar sign again in front of the number. That's the location of a value that you want to freeze. Freeze in place. Okay. Here, I'll illustrate with an actual spreadsheet here, and I can show you some other tricks real quick. All right, this will be available in Canvas if you want to use it. Again, please use your calculator because it will save you a lot of trouble. It'll expedite doing your homework. But there's more than one way naturally to do anything often. All right. This is a little bit too far away, so yeah. Turn this up here. And we'll zoom in. All right, now notice that the data values from the problem 74 through 83 are already here. All right, I have a second sheet that's adjacent right here. All right, just to illustrate. Let's say I put them in sort of out of order, right, as they originally were. 75 you would type, and it'll automatically be right justified. 81 was the next number. 83, I believe it was 78, and then 74, pardon me, 81, and then 74. All right. If you enter data in non-numerical order, you can tell it to basically organize this for you. All right, there's an option for sorting. Sometimes move these things. I believe it's over here. Where you see this looks like a funnel up in the corner here. If you highlight this and then press this, it should offer you some options in which order you want, from least to greatest or greatest to least. Notice that there's a little downward pointing arrow. Sort A to Z. I'm going to do this here. A to Z implies 1 to 26, right? So, smallest to largest. Expand the selection, continue with the current selection. Yeah, okay. There you go. And it automatically puts it in numerical order, 74, 75, 78, 81, 81, 83. So if you had a much longer list of random data, say it was imported from some appliance that you had that was measuring, all right, then you could spare yourself having to do that. That's the real point of my mentioning that. And again, you could go through this piecemeal if you wanted to, which is why I grayed out these blocks here. Remember, each one of the cells is a glorified calculator unto itself. You could make it do something. You could either just write simply a label in it like I wrote mean, or you could get it to function in some way like a calculator. Just hit equals first, all right? And if you want it to calculate an average, all right, you could do it brute force. You can tell it the location, or you could write the word average, all right? And then give it some coordinates. The coordinates is just highlighting from here to here. In this respect, it's from J4 to J9. Right? That's the start and the finish. Close the parentheses. And then it tells you 78.6 repeating. Right? If you want, you could also change how many digits are displayed here. And if you go the other extreme, it will round, right? Just visually, at least, superficially. The 78.6 repeating is approximately 78.7. If you wanted it to calculate a difference, all right, remember you're making it behave as a calculator. This isn't grayed out because you would need data values again. But you could do it brute force equals, right? I'm going to put a parentheses to highlight from here to here. Okay, we'll just do one at a time. Close the parentheses. Remember, this is like playing Battleship, you know. A letter and a number as an ordered pair, right? To and from, right? And then subtract, right, the value that is here. I'm going to just click on 78.7. Notice it gives the coordinates K4. The only problem is that if you were to get it to fill in the voids here and here, it's going to give you an error message if you don't put the dollar signs to more or less freeze this location. All right, I'll do it one time and you'll see it's okay. Negative 4.6 repeating. All right, but if I were to grab this little corner and stretch it down to here, all right, it's not doing the calculation correctly because it doesn't have all the information, right? So normally there's an error message. What I'm going to do is I'm going to go in here and I'm going to modify this. Up in the function bar here, you'll see the same thing that was originally typed in this place. If you click on it twice, it ends up showing you. Put a dollar sign in front of each of these things. All right, and that will still give you the same correct calculation for this first cell. All right, but it should allow you to get the information that is subsequent. All right, so you still have negative 4.666 repeating. And then when you grab this, it should automatically do those other calculations. And there you see, right? Good. All right. Negative 3.6 repeating. You could refine how much precision you want superficially. All right. I'm just curious what will happen if I go back to the mean here and stretch this out. All right. All right. Now, again, still doing this brute force. All right. You would next square each of these values from here to here. So again, treat it like a calculator at this point. These are just labels, all right, up here squared, and then I tried to describe it. And down here, these are behaving as a calculator. So you start with by pressing equals rather than ending by pressing equals. All right, and then you highlight the location of the data from start to finish, and in this case now it's column L, row 4, to column L, row 9. And you hit caret, upward pointing arrow, and then 2 to square it. All right, and there you have it, 21.7 repeating. All right. And then you could sum. All right, at this point I know the functions well enough to go, all right, I'm just going to add. But I have to tell it from where to where. So you go back here. Now, let me stretch this. I'm jumping the gun here. I should do one other thing first. Stretch. Those are the other squares. Now equals sum. Highlight this from here to here. And it gives you the sum of 65.3 repeating. All right. Again, if you just want the variance, all right, you're taking this location. You could put the dollar signs, but there is no other information anyway. And then hit divide, which is the forward slash. And then choose. Do you want a population or do you want a sample? All right. Let's go with 6, so we'll get a population, right? And you see that it's almost 11, right? If you want to calculate the standard, full-blown standard deviation, it's now to undo that step of squaring by square root. Square root is a function in the calculator as well, pardon me, in the software. It's squirt, S-Q-R-T, and then highlight this location, or you could type it if you like, and then it will spit out the value, 3.3. Now, down here you see the function, 3.6, right? That's the standard deviation of a sample, I want to say, right? If you just took the data from where it was originally located and type in STDEV, all right, it'll calculate standard deviation, all right? I'll do that here for the sake of matching. If this was, again, dependent upon a different number, 5, then you see that it would be, in fact, 3.6, all right? That's sample standard deviation, after having gone through the arduous process, and that's just using the function built in, standard deviation, right? If you wanted to get it of a population, I believe that would be another one of the choices. If you are interested in digging through Excel a little bit, sorry, I don't want to do that, all right, there are formulas here, all right, to choose from. Here are some examples: recently used financial, logical, text data, math and trigonometry. I think it would be financial is probably where it would be located. You see a bunch of these functions in here. And scroll through it. And if not there, then statistics. There we go. There you go. There's a lot of choices. All right. There's standard deviation, just as I've used it, STDEV. This is probably the distinction. I'm guessing .P is population and .S is sample. All right. Let me try with the .P instead. All right. I'm just curious, so I'll put it here. Equals. You could just type it, or you could click on the choices and then highlight where the data is located, and there you have it. It would be the 3.3. Yeah, that's a population. I'm just going to narrow this down. There you go. All right. This is, if you just use apparently STDEV, it's automatically of a sample. All right, even though they do have another one that just says STDEV.S. All right. And does the same thing. Yeah, there you go. It's preset. All right. If you want to specify, use the extra period apparently, .S or .P. Okay. But you don't have to go through the trouble is what I'm getting at. I only do this because it gets a person acclimated to using Excel spreadsheets, which are not hard. And the more you tinker with it, anybody can figure this out, I swear. What you just have to sort of accept is that there are labels. That is, you can just type something to make a nice table. All right. And then there are calculators, if you will. All right. You get them to function like a calculator by putting equals in it and knowing the functions well enough to, at least to choose from. All right, so it's good to know these, right? If you want to tinker with Excel, right? Average, and then the location you would write in here of the data. Sum is another one, and then the location of the data. Standard deviation, again, if you want to specify a sample or apparently a population, and then the location. The location is given in battleship coordinates, I mean the board game. Right? And if you want to freeze anything in place, as you would in a case like this, or in a case like this, all right, put $signs in front of the letter and number. And that will make that you, if you don't see that when you're trying to scroll through the extra calculations, notice one thing I did here. All right, I didn't really elaborate, but in order to get this extra junk that is down here, I just grab the corner with my mouse and then drag it down, and then it automatically, if you read any one of these, it automatically shifts location, right, and does the work, right. Notice what would happen. If I went past a certain point, you'll get an error message most likely if I went down here. Or it does, in this case, it just does zeros because there's no information to calculate from. Historically, it just goes into convulsions. And apparently, the people who run the software, they have improved that feature. Okay, so you're welcome to take this if you'd like it. That's not how you spell letter, that's with an R there. And use it for that purpose if you'd like. Okay? Tinker with it. You have to trust yourself that you could figure something out. Trust in your own self-efficacy. All right? It's very important. All right. Let me X out of here. No, I don't want to save this. All right. Let's go back to these questions. from the textbook now. We'll do these. All right, and then we're done. Okay. In this case, they're just asking you to calculate the amount of carbohydrates in grams, 10 different types of yogurt given below. Calculate the range, all right? You really should get in the habit, again, of putting these in numerical order first, all right? I know that's tedious, but do it, all right? It will help you if you have to answer any subsequent questions asking specifically about the median or have you, all right? So there's a bunch of 8s, and then there's a 9, and then it appears to be a 12 next, and then 16, and then 18, and then 19, and it gets easier as you cross stuff out, and then you catch yourself if you've made a mistake too, which is cool. Why it's a good technique. 29. Okay, now if you're just calculating the range, all right, and you've put it in numerical order, this is the low figure, and this is the high figure. Right? So just a very rough idea of the spread of the data, how far apart the extremes are. All right, it would be 29 minus 8, which would be 21 apart. All right. And this is the unit of grams. All right, 21 grams apart difference. All right, from one extreme to the other. Right. If again you're going to calculate the standard deviation, definitely want to use your calculator, right? Because as you know, it's a tedious process, and if you've done it by hand, you appreciate that. Even if you've done it in Excel in the very piecemeal way that I illustrated, you can see it's tedious. It takes a lot of time. A veterinarian is in an animal hospital recorded the following lifespans of selected Labrador retrievers to the nearest year. This is not quite in numerical order, but very close. All right, here's 12. All right, that's not a 2, that's a 12. In between, all right, determine the standard deviation of that. Again, go through the process, take your calculator, and clear out the old data. All right, so hit second, scroll over to that. And you're already in one variable statistics, so you hit data, and now you enter 7, 9, 11, 12, 15, 18. All right. 7, scroll down, 9, scroll down, 11. That's 33, ding dong. Okay, sorry, delete. 11. 12, 15, 18. Okay, so let's just verify because I'm doing it backwards here. 18 is the 6th piece of data, 15, 12, 11, 9, and it should be 7. Good. Now you hit stat var, you have 6 pieces of data. Here's the mean if you were interested, 15. And the sample standard deviation is 4, and the population is a little bit more precise. It's 3.65, almost 3.7. Okay. All right. Okay. So this is approximately. Well, it's 4 if you just go for the sample. Okay. And this is essentially the same thing here. All right, you're just using a different set of data. What you should get doing these, which they're already in numerical order, which is cool. All right, your standard deviation in this case should be $27.01. same process. Clear out your calculator and input these instead. All right, the following are the prices of 9 stocks on the New York Stock Exchange. Determine the standard deviation of the prices. Assume that they want a sample unless they specify otherwise. All right, and again, if you have a true standard deviation rather than variance, you have the unit that you want. We're thinking of dollars as a unit rather than, it's dollars degree 1 rather than dollars degree squared, right? Okay. All right, and that's basically it. All right, so think of this section as getting well acquainted with your calculator. Because when you get to section 12.6 especially, you definitely want to use your calculator, trust me. All right, for homework, do section 12.4 in my lab, and then you're good. Good to go. Okay? All right, thank you guys for sticking with me. I'll see you again on Monday. Be careful out there.